So in this video, we will be learning about limits. A limit is the behavior of a function when it is near a point, not at the point, but when it gets really close to that point. So in case you didn't understand what I'm saying, we will look at this function in the example. We have f of x equals to 3x minus 2 divided by x squared minus 4. So we want to know what happens as the function gets really close to the point x equals to 2. So what we will do is we will take values that are very close to 2. We will take values a bit less than 2, as you can see in this table on the left, and other values that are a bit larger than 2, and we will try to get closer and closer to 2. So let's start with our first value, 1.9. So 1.9 is a value that's close to 2. So we will plug in 1.9 in the function f of x. So we will do f of 1.9 is equal to 3 times 1.9 minus 2 divided by 1.9 squared minus 4. And if you plug in this on your calculator, you will get 0.769. Now let's try another value. Same process. Plug it in the function. And if you plug it in on your calculator, you will get 0.759. We will continue with values that get even closer to 2, such as 1.99. Plug it in and you will get 0.752. The last value we will take that's a bit less than 2 but really close to 2 is 1.9999, and this will give approximately 0.75. So as you can see, the closer we get to 2, the more the value gets close to 0.75. This value here is rounded. It's not exactly 0.75, but you can see it's getting closer and closer to 0.75. Now let's look at values that are a bit larger than 2. So let's look at 2.1. So if we do f of 2.1, this is 3 times 2.1 minus 2 divided by 2.1 squared minus 4. And plug it in on your calculator and you will get 0.732. Let's try 2.05. You will get 0.740. Let's try 2.01. You will get 0.748. Now a value that's even closer to 2, so let's try 2.0001, and this gives 0.74998. So as you can see, the more we're getting close to 2, the more the value is approaching 0.75. So this brings us to the definition of a limit. Again, please note that whenever I put a book number in a page number in parentheses, these images, exercises, and questions, and sometimes definitions come from the book. So, suppose f of x is defined when x is near the number a. This means that f is defined on some open interval that contains a, except possibly at a itself. Then we write limit x approaches a of f of x equals to L. And we say the limit of f of x as x approaches a equals L if we can make the values of f of x arbitrarily close to L, or as close to L as we like, by restricting x to be sufficiently close to a on either side of a but not equal to a. So, in case you did not understand this definition, basically, if we were to use the wording of the definition in our example here, this is the limit as x approaches 2 of f of x. In this case, where they referred to a in the definition, or our a in this example is 2. We are getting really close to 2, we are approaching 2, and as we get close to 2 from both sides, the value of f of x is getting close to 0.75. Now, if you remember in the previous exercise, we were looking at what happens to the function as we approach 2 from the left side, or from values that are slightly less than 2 but very close to it, and from the right side, or from values that are slightly larger than 2 but very close to it. So this brings us to another definition, which is the one-sided limit. We write limit of f of x as x approaches a from the left equals to L, and say that the left-handed limit of f of x as x approaches a is equal to L if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a with x less than a. We write limit of f of x as x approaches a from the right equals to L, and say that the right-hand limit of f of x as x approaches a is equal to L if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a with x greater than a. So in our case above, we were making x, in the first table here, we were making x close and closer to 2, but with values slightly less than 2. So if we were to write that, we were doing limit x approaches 2 from the left. So we put a little negative sign, which signifies that this is from the left of f of x, and we were getting closer to 0.75. And in the table on the right, we express this as limit x approaches 2 from the right, so we put a little plus sign, f of x. The function also was approaching 0.75, so the limit is 0.75. Now let's look at a few graphs so that we can practice what we just learned. So, in this graph, we will look at the limit of f of x as x approaches 2. So let's highlight what we're doing. So we're getting really close to 2. And we also notice that f of x becomes close to the value 3. And we can do this from both sides, and we realize that we are approaching 3. So, limit f of x as x approaches 2 is 3. Now let's look at this graph. We would like to know the limit of f of x as x approaches 4 from the left. So let's get closer to 4 from the left side. And that's where we hit 4. And we realize that the function is closer and is close to 1. So the limit as x approaches 4 from the left of f of x is 1. Now let's go from the right. We would like to get close to 4, and this is when the function gets close to 2. So the limit x approaches 4 from the right of f of x is 2. Now, what happens if we would like to find the limit as x approaches 4 of f of x? Because we have an issue here. If we go from the left, the limit is 1, but if we go from the right, the limit is 2. And in such a case, the limit as x approaches 4 of f of x would not exist. So we write D and E for does not exist. So limit f of x as x approaches a equals to L if and only if limit f of x as x approaches a from the left equals to L and limit f of x as x approaches a from the right equals to L. So basically from both sides we're like both limits should give the same answer in order for us to have a limit that exists. So far we were looking at limits that give answers in the real numbers. Now we will look at a little more complicated graph. So let's look at this graph. We would like to find the limit as x approaches 0 from the left of f of x. Suppose this is f of x. So we will get close to 0, but we don't touch 0. And we notice that this function will keep on increasing upwards, but it never touches x equals to 0. So in such a case, because we know it will keep on going up and up, it will keep on increasing. In such a case, the limit as x approaches 0 from the left of f of x is infinity. Now if we approach it from the right, let's get closer to 0, as close as we can, and we also notice that the function will keep on increasing. In such a case, the limit of f of x as x approaches 0 from the right is also infinity. Therefore, the limit of f of x as x approaches 0 is infinity, because we notice that both of these, of the left-hand limit and the right-hand limit both gave infinity. So the limit f of x as x approaches 0 is infinity. And whenever we get an answer that's not a real number, so whenever we get infinity, we can say that the limit diverges. So let's look at this definition. Let f be a function defined on both sides of a except possibly at a itself. So let's look up again. F of x is defined on this side of a, on the right side, and on the left side, but at x equals to a, so in our case a is 0, we have an asymptote here. So it is not defined at x equals to 0. Then limit of f of x as x approaches a equals to infinity means that the values of f of x can be made arbitrarily large as we please by taking x sufficiently close to a but not equal to a. So as we can see, the value of f of x will keep on getting larger and larger as we get closer to 0, but not at 0, because at 0 we have an asymptote. So the same definition or a similar definition is true if we had a function like this. In such a case, the values of f of x are approaching negative infinity as we approach as x approaches 0, so the values can be made arbitrarily small as x approaches 0. Now let's look at another example. Limit x approaches 0 of 1 over x. So it never hurts to draw a graph. So let's draw the graph. And this is the graph of f of x equals to 1 over x. So the limit as x approaches 0, how do we find it? So first of all, we notice that as we approach 0, the right hand goes like from the right hand side, the graph is going upwards, but from the left side, it's going downwards. So in such a case, we can split the limit. So we can do the left hand side on its own and the right hand side on its own. So let's start with the left hand side. As x approaches 0, the graph is getting smaller, 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 and smaller. And in such a case, as we mentioned earlier, it's equal to negative infinity. However, when we're approaching when x approaches 0 from the right, the function gets bigger and it will keep on increasing, and in such a case, we write limit of 1 over x as x approaches 0 from the right is positive infinity. And then we notice that the left-hand limit is not equal to the right-hand limit. We can write that too. Because of that, the overall limit of 1 over x as x approaches 0 does not exist. And there is a general rule. So the limit of 1 over x to the power of n as x approaches 0 has two cases. So if n is odd, it's equal to infinity if we're approaching 0 from the right, and it's equal to negative infinity as we're approaching 0 from the left. So we can look at this example. In this example, the function was 1 over x, which is the same as 1 over x to the power of 1. So n is equal to 1, n is odd. So as we approached 0, as x approached 0 from the right, the limit was infinity. However, as x approached 0 from the left, the limit was negative infinity. And in such a case, since from both sides we do not get the same answer, then the limit does not exist. However, when n is even, the limit as x approaches 0 of 1 over x to the power of n is equal to infinity. An example would be this graph we drew up here. So this graph is a graph of 1 over x squared. So we see this power, n equals to 2, n is even. So the limit as x approaches 0 of 1 over x squared equals to infinity. Now, just as a reminder, I already mentioned this. Whenever the limit of a function equals to positive or negative infinity, we write after it that the limit diverges. However, if the limit gives a real number, then in such a case, the limit converges. Now we will move on to some properties of limits. If we have two functions f of x and g of x, and we are told that both the limit of f of x as x approaches a and the limit of g of x as x approaches a, both of these exist. So, the first property is the limit of f of x plus g of x as x approaches a is the same as limit of f of x as x approaches a plus limit of g of x as x approaches a. So for instance, if f of x equals to x squared and g of x equals to 2x, so the limit as x approaches 0 of f of x, which is x squared, plus g of x, which is 2x, is equal to the limit as x approaches 0 of x squared plus the limit of 2x as x approaches 0. Now let's look at the second property. The limit of f of x minus g of x as x approaches a is equal to the limit of f of x as x approaches a minus the limit of g of x as x approaches a. So this is the same concept as what we just did in property 1. So the limit of x squared minus 2x as x approaches 0 is the same as the limit of x squared as x approaches 0 minus the limit of 2x as x approaches 0. Now, the limit of a constant times f of x as x approaches a, we can take the constant out, so it becomes the constant times the limit of f of x as x approaches a. For instance, if I want the limit of 2x squared as x approaches 0, this is the same as 2 times the limit of 2 times the limit of x squared as x approaches 0. Now if I want the limit of f of x times g of x as x approaches a, this is equal to the limit of f of x as x approaches a times the limit of g of x as x approaches a. So the limit of x squared times 2x, which I can write as 2x cubed, as x approaches 0, is the limit of x squared as x approaches 0 times the limit of 2x as x approaches 0. Property 5. The limit of f of x divided by g of x as x approaches a is equal to the limit of f of x as x approaches a divided by the limit of g of x as x approaches a, if the limit of g of x as x approaches a is different than 0. For instance, the limit as x approaches 1 of f of x divided by g of x, so f of x is x squared and g of x is 2x, this is equal to the limit x approaches 1 of x squared divided by the limit as x approaches 1 of 2x, and you might notice that in the entire 4 properties before, I was using x approaches 0 and now I changed to x approaches 1, because we will learn later during this and the next videos that the limit, I will write this, the limit of 2x as x approaches 0 is equal to 0. We will learn how to compute this later, but I'm just showing you whenever the limit is equal to 0, we cannot use property 5 because the denominator cannot be 0. Now let's move on to property 6. The limit of f of x all to the power of n as x approaches a, we can take the power outside. It becomes the limit of f of x as x approaches a all to the power of n, where n is a positive integer. So an example is, let's say, limit of x squared all cubed as x approaches 2. We can take the cube outside, so this becomes the limit of x squared as x approaches 2 all cubed. Now let's move on to property 7. The limit of nth root of f of x as x approaches a is the nth root of the limit of f of x as x approaches a. So we can take the root outside. An example might be limit of x squared plus 5 as x approaches 2 is equal to limit of x squared plus 5 as x approaches 2, and then I square root the entire thing. And please notice that here, whenever I have two two terms, x squared and 5, put them in parentheses to make it clear, to make clear the limit of what you are taking. Finally, the limit of a constant as x approaches a is the constant in itself. So the limit of 1 as x approaches 0, we do not have any x in the expression, so the limit is equal to 1. Now the limit of x as x approaches a is equal to a, so the limit of x as x approaches 1 is equal to 1. So these are some important limit laws which we will be using later on to solve limits. So the first technique we will use in order to solve limits is the direct substitution method. As the name suggests, it's literally directly substituting. So we are plugging in a. Basically, in the first example, we are used to writing usually x approaches a, so our a is 0. All we have to do is wherever we see an x, here and here, we plug in a. So this gives us, instead of x cubed, 0 cubed plus cosine 5 times 0 over 10,000, which is equal to cosine 0 over 10,000, which is equal to 1 over 10,000. And this is our answer. Now let's move on to another example. In this case, x approaches 5, so anywhere we find an x, we replace it with 5. So this is equal to 2 times 5 squared minus 3 times 5 plus 4. You can plug this in on your calculator, and this gives 39. And as you can see here, we are getting real numbers as our answers. So whenever we have a polynomial or a rational function, and a is in the domain of f, then the limit of f of x as x approaches a is equal to f of a. So as you can see, a equals to 0 in the first example. It is in the domain of this function, and this is why we can plug in a, or we can plug in 0. Same for this example here, it's a polynomial, and x equals to 5 is in the domain, therefore we can plug it in. Now let's take a look at this exercise. We are told to use the limit laws and the graphs of f and g in figure 1 to evaluate the following limits if they exist, and this question is also from the book. So, part A, limit of f of x plus 5g of x as x approaches negative 2. So as we learned earlier, the limit as x approaches negative 2 of f of x plus 5g of x, we can separate these because we have addition in between, so this becomes limit of f of x as x approaches negative 2 plus limit of 5g of x as x approaches negative 2. And then we have a constant in front of g of x, so we can take this constant outside the limit. So this becomes 5 times the limit of g of x as x approaches negative 2. Now let us find these limits. F of x is in red. So as f of x approaches negative 2, which is here, Let us look from both sides. So as it gets closer from the left, it gets really close to 1. And as it gets closer from the right, it gets really close to 1 as well. Therefore, the limit of f of x as x approaches -2 is 1 plus 5 of the limit of g of x as x approaches -2. So let's check what this limit is. So -2 is somewhere around here on g of x. So as we get close to it from the left, we are really getting close to the value of -1. And as we get really close to it from the right, we are also getting close to -1. So the limit is -1. So 1 minus 5 equals to -4, and this is our answer for part A. Now let's move on to part B. Limit x approaches 1 of f of x times g of x. Again, using limit laws, we can separate this into limit f of x as x approaches 1 times limit of g of x as x approaches 1. So let's find each limit. So as f of x approaches 1 from the left, we are getting really close to this value of 2. And as f of x approaches 1 from the right, we are also getting really close to the value of 2. So the limit of f of x as x approaches 1 is 2. Now let's look at g of x. So the limit of g of x as x approaches 1 from the right is -1. As you can see, we're going from the right, we're approaching x equals to 1. We get really close to the value of -1, so I will write this down. The limit as x approaches 1 from the right of g of x equals to -1. And now let's look at from the left. The limit as g of x, the limit of g of x as x approaches 1 from the left, we notice that this is close to -2. And what can we conclude in such a case? That the limit of g of x as x approaches 1 does not exist because the left-hand side limit and the right-hand side limit are not equal. So in such a case, we cannot compute the limit of f of x times g of x as x approaches 1. But what we can do instead is we can compute one-sided limits. So let's see how we will do this. So instead of computing limit x approaches 1, we will compute limit x approaches 1 from the left, f of x times g of x, and this is limit of f of x as x approaches 1 from the left times limit of g of x as x approaches 1 from the left. Regarding f of x, we already said that it is 2. And for g of x, as x approaches 1 from the left, the answer is -2. So 2 times -2 is -4. Now let's compute the right-hand limit. So limit of f of x times g of x as x approaches 1 from the right is limit of f of x as x approaches 1 from the right times limit of g of x as x approaches 1 from the right. And again, for f of x, we already concluded that the limit gives 2. And for g of x, as x approaches 1 from the right, the limit gives -1. So our answer is -2. And we can write a conclusion. Limit f of x times g of x as x approaches 1 does not exist because the left-hand sided limit does not equal the right hand side limit. And this would be our answer for part B. Now let's look at part C. The limit of f of x divided by g of x as x approaches 2. So we have a property of dividing. So we can say that the limit of f of x as x approaches 2 divided by the limit of g of x as x approaches 2. However, this only works if the limit of g of x as x approaches 2 is different than 0. So let's look at our graph. As g of x approaches 2, 2 is here on the graph. We can notice that from the right hand side it gets really close to 0, and from the left hand side it also gets really close to 0. So in such a case, the limit of g of x as x approaches 2 is equal to 0, so we cannot use this property. Now we will proceed to another technique of finding limits, which is factoring. It never hurts to factor whenever you can. So let's take a look at this example. Limit of x squared minus 1 divided by x minus 1 as x approaches 1. So you might ask, why aren't we using the direct substitution property, which we learned a few minutes ago? So the reason was that we agreed that we can use it when a, in this case when 1, if it is in the domain of the function. So if we take a look at this function, we can notice that if we plug in 1, we will get a 0 in the numerator and a 0 in the denominator, which shows that it is not in the domain of the function. Because of that, in order to know which technique to use, always you can try, start by plugging in. And write your answer on the side, do it really quickly and write your answer on the side. So in this case, if we plug in, we would get 1 squared minus 1 over 1 minus 1, which is 0 over 0. So just write it in little brackets on the side, write 0 over 0. And this 0 over 0 would be a sign to you that you should use another technique other than plugging in. So today, in this example, we will learn about factoring. So let's try to factor the numerator. As we learned in previous videos, when we have a squared minus b squared, this we can factor to a minus b times a plus b. In our case, we have x squared minus 1 squared, we can factor to x minus 1 times x plus 1. So we write this in the numerator, and we write the denominator, and then we cancel out the x minus 1. This leaves us with limit of x plus 1 as x approaches 1, and now we can try to plug in to see what we get. If we plug in, we get 1 plus 1, which is equal to 2. And this is a real number, it is our answer. Let's move on to another example. Limit of 3 plus h all squared minus 9 divided by h as h approaches 0. So let's try to plug in. If we were to plug in, we would get 3 plus 0 squared minus 9 divided by 0. So this is 3 squared minus 9 over 0, which gives us 9 minus 9 over 0, which is 0 over 0. So on the side, keep it written 0 over 0. So this is a sign that plugging in is not the right technique in this question. So we might try another technique. So we can try to factor. Again, as I showed you earlier, a squared minus b squared is a minus b times a plus b. In our case, this is a, and b is 3, so b squared is 9. So if we were to factor this becomes a minus b times a plus b divided by h. Now always simplify. So 3 minus 3, we cancel out the 3's. So this becomes limit h approaches 0 of h. 3 plus 3 is 6 plus h divided by h. And now we cancel out the h, so this is limit h approaches 0 of 6 plus h. And now we can try to plug in. So this gives us 6, which is a real number, so it is our answer. Now we will move on to what if we had an absolute value. So maybe it doesn't hurt to draw a graph of the absolute value function. And if you can notice that on the right, the absolute value function is y equals to x, and on the left it's y equals to negative x. So if we were to take the limit of absolute value of x divided by x as x approaches 0, we can divide this into two different limits. So we can do limit as x approaches 0 from the left of this function and limit as x approaches 0 from the right of this function. So what happens from the left, as you can notice on this graph, I'm getting really close from the left. As you can notice, instead of writing absolute value, I can write the function y equals to negative x, because this is the function as I'm approaching from the left. So I can write this as negative x over x. This is as if I'm saying negative 1x over x. So I can take the constant outside, and I am left with limit negative 1 times the limit of x over x as x approaches 0 from the left. I can cancel both of these x's. This becomes negative limit as x approaches 0 from the left of 1. And the limit of a constant is the constant itself. So this gives us a final answer of negative 1. Now let's look at the limit from the right. So if we look at the graph again, if I'm going from the right-hand side, the function is y equals to x. So instead of writing the absolute value, I can write x. And now I can simplify. This gives me the limit of 1 as x approaches 0 from the right, and the limit of the constant is the constant itself. And as we can notice from these two limits, that the limit as we approach the function from the left is not equal to the limit as we approach the function from the right. Therefore, the overall limit of the absolute value of x divided by x as x approaches 0 does not exist. And this is the technique which you should always use whenever you are dealing with absolute values. So this is another function with an absolute value. We might as well use the same technique. So the limit, so this is equal to the limit. We will take the left-hand sided limit first, and then we will take the right-hand sided limit. So now what should we put in the denominator? For the right-hand sided limit, as we did above in the previous example, we left the function the same. But for the left-hand sided limit, we took the negative of the function. Now let's work one by one. So, again, you can always plug in if it helps you. And you might notice immediately that if you plug in, 2 is not in the domain. So plugging in will not give you like the right answer, but let's try it. So if we plug in, we will get 2 squared plus 2 minus 6 over negative of 2 minus 2. That's for the left-hand sided limit. So this is 4 plus 2 minus 6 over negative 2 minus 2. So 4 plus 2 is 6 minus 6. This gives us 0 over 0. So you can write this somewhere, and you will get the same thing from both sides. So whenever you see 0 over 0, this should be a sign immediately that you should factor. You should try to simplify in some way. So we have a quadratic in the numerator. We can factor it to x minus 2 times x plus 3. For a review about factoring, you can check out previous videos. And I forgot a negative sign here. So this is what we end up with. And let's work with the left-hand sided limit. We cancel out the x minus 2. And we have a constant. We can take it outside the limit. This gives negative limit of x plus 3 as x approaches 2 from the left. So now we might try to plug in 2 plus 3. So this gives us negative 5. Now for the right-hand side, we can cancel the x minus 2. This gives us limit of x plus 3 as x approaches 2 from the right. And now we can plug in. This gives us 5. And we can notice that the limit of the function, I will name it f of x, the left-hand sided limit is different from the right-hand sided limit. So the overall limit of f of x as x approaches 2 does not exist.